So our most important congruence criteria results in geometry relate to congruence criteria for triangles. So we're going to take a look at the various possibilities for what subset of information that we need in order to guarantee that two triangles are congruent, especially as they relate to the lengths of the triangle's sides and the measures of the triangle's angles. So the question we're going to ask is, under what circumstances are two triangles guaranteed to be congruent? Let's look at some possibilities. First, suppose that all of the sides of a pair of triangles are congruent one to another. We call that the SSS criteria. So let's suppose that I tell somebody, here's 3 sticks of length 1, 2, and 4, build me a triangle. The question is, if two different people build a triangle using the same set of sticks, will their two triangles be guaranteed to be congruent to one another? Well, the only problem with SSS is that just picking up a random pair of 3 sticks does not always give us a valid triangle at all. Imagine if I situate the triangle, the segment of length 1 up at the top and the 4 going down the side, then my little segment of length 2 doesn't quite reach the end, reach the little vertex at the end of this triangle right here on our triangle. And so it's not actually possible if we try, no matter how hard we try with this set of 3 segments, we can't actually connect them together to form a triangle. And the reason is that that stick of length 4 is just too long for the sticks of length 1 and 2 to be able to reach all the way from one end of it to the other. After all, if we take the sticks of length 1 and 2 and we lay them end to end on top of my stick of length 4, even laying them end to end isn't going to reach me from one end of that segment to the other. So because 1 plus 2 is less than 4, it's impossible for us to make a triangle out of this set of 3 lengths. So that's a manifestation of what's called the triangle inequality. The triangle inequality says that if we have a valid triangle, PQR, then the sum of the lengths of 2 connected sides, so in this example, let's say PQ added to QR, that sum has to be at least as large as the length of the third side, PR. This is sometimes thought of as the shortest distance between 2 points is a straight line type of an inequality. The shortest way to get from P to R is to go on a straight line from P to R rather than on a straight line from P to Q and then a straight line from Q to R. So unless our lengths of segments satisfy the triangle inequality, we can't make a triangle out of them at all. So it's for that reason that we're going to think of the side-side-side set of criteria. Even though it does guarantee us a congruent triangle, as we'll see, it's not the most natural criterion to start with. We're going to treat SSS like a theorem, not an axiom, something that we have to deduce, not something that we can assume and proceed from. So if that's the case for 3 sides, what about 3 angles? If I have a triangle whose angles are exactly the same as another triangle, are those 2 triangles guaranteed to be congruent? Let's try it. So here are a pair of triangles that are built out of the same angle measures. So angle P is the same measure as angle S, so those angles are congruent. The angles Q and T are congruent, and the angles at R and U are congruent. So the angles are all the same. But I've deliberately drawn this figure, presumably to scale, so that I have a triangle on the left, which is smaller. The lengths of the sides are smaller than the lengths of the sides of the triangle on the right. And so these 2 triangles are not congruent. Equality of angle measures does not guarantee congruence of the segments, the lengths of the sides. So AAA is not, in fact, a criterion for congruence at all. All right, so what about mixing angles and sides? There are 2 different ways to do that. One of them is to pick 2 sides and 1 angle. So this would be like giving me 2 sticks, maybe length 1 and length 3, and then also giving me an angle, and saying make me a triangle that uses these 2 sticks as sides and also has this angle as one of the angles. Now whether or not we can do this depends on how we arrange the sides and the angles with one another. If I place the known angle in between my 2 known sides, then we get what's called an SAS criterion, or side angle side. What that would look like is to place the angle down on the table, and then place one of my sticks along one side of the angle, my other stick along the other side of the angle, and then just sort of connect the dots at the ends of those segments to form my third side. So here's one way to do that, where I've put my shorter stick on the side above the longer stick in my 45-degree angle and then connected the dots. But there's only really one other way to do that after I've placed my angle down on the table, and that's to put the longer stick on top of the shorter stick, and then connect the dots once again. So now I have two different triangles that are both have the same side angle side sequence. Are these congruent triangles? I'm going to claim that they are. And the reason that they're congruent triangles is I can check that the segment AB corresponds exactly with the segment PR. Those are congruent. Likewise, AC corresponds with PQ. Those are congruent sides as well. And the angle at P and the angle at A are congruent one to another. And it shouldn't take too much reflection, we'll see why this is true, but actually we're going to take this as an axiom, to guarantee that BC and QR are actually also congruent segments as well. And if all of those segments are congruent, then because SSS is a congruence criterion, we'll be able to guarantee that these are congruent triangles. But again, that's getting the directionality backwards. It turns out we're going to take SAS as our axiom and deduce SSS as a theorem. But hopefully this short exercise can convince you heuristically at least that if I place my known angle in between my two known sides, then I'm guaranteed to get a unique triangle up to congruence. The story, however, might be different if I change the ordering of the two sides and my angle. If I connect the two sides to each other first, and then I attach the known angle at one of their ends, let's see what might happen. So for this, I'm going to choose different side lengths. I'm going to choose 4 and 5 instead of 1 and 3, but I'm going to keep my 45-degree angle. So one way of making a triangle that has a side of length 4 connected to a side of length 5, and then an angle of 45 at the other end of that segment of length 5 is shown right here. So if I connect the third side down there, then I'm going to get one triangle. But now imagine that we take that purple segment of length 4 and we just sort of swing it, so pivot it along the hinge point at the point A on the top. So that instead of connecting the way that it connects, we sort of swing it over to the left and connect it this way instead. It has the same length, 4, but now I've created a different angle down there at the bottom of my triangle. My 45-degree angle on the left remains. My segment of length 5 on the other side of the triangle remains. So I still have a 4 segment connected to a 5 segment connected to a 45-degree angle. But I think it's pretty clear why these two triangles are not congruent to one another, because those angles that are opposite the segment of length 5 do not have the same measure. In fact, one of them is acute in the triangle on top. It's less than 90 degrees. The other is obtuse. It's greater than 90 degrees in the triangle on the bottom. So SSA then is not a criteria for congruence, because given two sides and an angle in sequence in that way, it's possible in some cases for me to come up with two non-congruent different triangles that satisfy that same SSA. So SAS will be a congruence criterion for us, but SSA can absolutely not serve that function. The last combination then is two angles and one side. Let's think about what it might look like to give somebody a pair of angles and one stick, so a known side and two known angles, and ask them to build a triangle out of that. One way to do that is to place the known side in between the two known angles in what we call an ASA sequence. So for that, I'm just going to lay my stick down on the table, place my two angles at either end of the stick, and then to figure out where the other vertex of my triangle is, I just have to extend those angles and find out where they meet. So here's one way of doing that. If I put a 45-degree angle on the left side of my 3 stick and a 30-degree angle on the right side of my 3 stick. Well, the only other way to do that is to place my 30-degree angle on the left side and 45-degree angle on the right side, extend those angles and find out where they meet. But a moment's reflection should be all you need to convince yourself that these two triangles are in fact congruent, that ABC and RQP are correspondingly the same segments, and therefore we have a congruent triangle. Okay, so ASA is a congruence criterion. What if we place the angles together and the side at the end, AAS? What that might look like is I place an angle down on the table. There's my 30-degree angle. And then I place my 3 stick down on the table at a 45-degree angle to where the base of my 30-degree angle was. And I try to figure out how to do that in such a way that that 3 stick meets the ray that I drew going up from my 30-degree angle. There are a variety of places that I could place my 3 stick to make a 45-degree angle, but I want the one that exactly meets my 30-degree angle ray as well. And you should be able to convince yourself here that there's only, in fact, one way to do that. There's only one way of drawing this triangle that has these 30 and 45-degree angles connected by a variable length side, and a segment of length 3 that's fixed on the right-hand side here. So in fact, it turns out that AAS, unlike SSA, will be a congruence criterion for us. So here we have a whole bunch of different criterion that are going to guarantee congruence of triangles. And what we'd like is we'd like not to have to prove each one of them in isolation. What we'd like to know is which ones of these follow from which other ones. Because SSS was not a natural criterion for congruence, because not every collection of three sides even gives us a possible triangle to begin with, we're going to treat SSS as though it's a consequence of something else. It's not going to be our axiom. Instead, we're going to deduce the truth of SSS from something else. And something else that we're going to deduce it from is SAS. So the SAS congruence criterion for us is going to be the one that we're going to take for granted as an axiom. So it will be axiomatic for us, not something we have to prove, but something we take on faith that if two sides and the angle in between them are congruent in two triangles, then those triangles are congruent. That will be our axiom, and from that axiom, we'll be able to deduce SSS, ASA, and AAS, all as theorems guaranteeing that two triangles are congruent.